So good evening, everyone. No, sorry, good evening. Good morning, everyone. It's not even afternoon. I'm saying evening. Good afternoon, everyone, and welcome to this lecture. This is current electricity, and we are dealing with lecture number 2 in current electricity. Now, in the previous lecture, we had seen what was current. Yes or no? We had
Sir.
seen current is the rate of flow of charge, and we had seen the two types of current: average current, total charge divided by total time; instantaneous current, rate of flow of charge. We had also seen the direction of current, and you should never remember, you should always remember what is the direction of current taken as. We call it conventional direction of current flow. What is the direction of current taken as? Huh?
Positive.
What positive? Huh? What positive? Direction of current is taken as what? See, they
Opposite
don't.
to electron.
Huh?
Along the direction of electric field.
Along the direction of. See, don't remember. Write it. Write it. Direction of current is taken as the direction of the conventional direction of current is nothing but the direction of flow of positive charges. Please write it. Tend to forget. This is the direction of flow of positive charges. And this is also opposite to the direction of flow of negative charges. The direction of flow of current is the direction of flow of positive charges, which is same as the direction of electric field. You can also write it here, same as the direction of electric field, or it is opposite to the direction of flow of negative charges. I hope that we will remember it. Do we understand this? Yes or no? No, yes. Will you remember this? Yes, sir. You don't remember
Yes,
it,
sir.
sir. That is the problem, sir. That gives me problem, sir. Please remember it, sir, because these questions are going to come in your exam. The exams are very near. Let's start today's class with this question. We are continuing on our journey of understanding current, and this is the first question that we are going to do. Remember, this question has been repeated a number of times. In the Bohr's model of hydrogen atom, the electrons move around the nucleus in a circular orbit whose radius is given as 5 into 10 raised to the power minus 11 meters. The time period, the time period is 1.5 into 10 raised to the power minus 19 seconds, my dear friend. What is the current associated with this? How much is the current that we can say is flowing? I will give you 2 minutes and 2 minutes only, and I expect to get an answer. Can I get an answer? Yes or no? Will I get an answer?
Yes, sir.
Well done. I'll give you 2 minutes. Let me know once you have the answer. Well, then we need to go ahead and solve this question. How are we going to solve this question?
So,
The radius of the orbit is
option
given
D.
as 5 into 10 to the power minus 11
Sir,
meter, and the time period is given as 1.5 into 10 to the power minus 16 seconds. Yes.
sir. Sir, option D.
Option D. It should not have taken so much of time. Yes, it is option D. How are you supposed to find out the current in this wire? It is very simple. The time period is given. I told you, if the time period is given, current is whatever charge is moving divided by the time period. The charge is nothing but the charge of an electron. They will not give you the charge of an electron. You must know it. 1.6 into 10 raised to the power minus 19 coulombs divided by the time period 1.5 into 10 raised to the power minus 16. Remember, this is NEET. You don't have to calculate it. Once you know that it is 1.6 into 10 raised to the power minus 19 divided by 1.5 into 10 raised to the power minus 16, you look at the options. See, in one option, the answer is given as 10 raised to the power minus 19. In one option, it is given as 0.17. In one option, it is given as 10 raised to the power minus 3. You can very easily understand that you are going to get 10 raised to the power minus 3 from here. So you don't even have to calculate. And you can straight away say that the answer is going to be 1.07 into 10 raised to the power minus 3 amperes. And that, my dear friend, is the correct answer. You should have gotten it quickly. How many of you got it? Boys, did you get it or not? Well, I'm not getting any response. Please try and use your knowledge in the right way. And I'm sure you will be able to get the answers quickly. Remember, you have to solve 45 questions, 50 questions, 45 in a span of 60 minutes. You have to do them quickly. And that is why we are only doing those questions which are going to come. This is the next one, and I hope that you can give me the answer for this one. Here comes the question. This is the next question. An electron is moving in a circular path of radius 1.5 into 10 raised to the power minus 11 meters. Radius is given. Frequency of 6.8 into 10 raised to the power 15 revolutions per second. The current is how much? The current is how much? I'll give you 2 minutes to solve this question. And I hope that you can give me an answer quickly and correctly. The 2 minutes starts now, my dear friends. Please try. Option C is correct. That is correct. How did you get the option? Frequency is given, my dear friends. Frequency is given. So frequency is given. Frequency is given. And frequency is 1 by T. Yes or no? So that is given as 6.8 into 10 raised to the power 15 revolutions per second. So from here I can get the value of 1 by T. You must know that current is total charge divided by the time period in this case. So it becomes how much? Q, the charge of an electron, 1.6 into 10 raised to the power minus 19 divided by T is same as multiplication by 1 by T. So basically I just multiply this by 6.8 into 10 raised to the power 15, and then you can easily see which option you will get. Which option are you going to get from here? That would be option C. You just have to multiply 1.6 by 6.8 and you will get the answer. Do we understand this? Yes or no? Do we understand this, everyone? No? Do we understand this?
Yes, sir.
Everyone? Okay. Then I'll give you one more question on this. And if you are able to do that, that means you can do any question that comes from this category. Remember, the questions in this category may have some calculations. You have to get to the answer fast. And you can also look at the option and get an idea of what sort of an answer you would be getting. This is the next question, my dear friends. In a neon discharge tube, 2.9 into 10 raised to the power 18 Ne, neon plus ions move to the right each second, while 1.6 into 10 raised to the power 18 electron move to the left towards second. The charge of an electron is 1.6 into 10 raised to the power minus 19 coulombs. What is the current in the discharge tube? That is the question. It's a simple question. I hope you understand the meaning of this question. I'll give you 2 minutes to give me the answer. Your time starts now. I hope you have tried the question, and let us move and solve this question. How are you going to solve this? Any idea? Now you can see this neon plus ions are positive and they are moving towards right. So they are moving towards right like this. And it is given each second. So basically it is current each second. Charge per unit time. Basically how much charge is moving. These many neon plus charges are moving towards right each second. Now 1.2 into 10 raised to the power electrons are moving to the left. So these electrons are moving towards left, and positive charges are moving towards right. Positive charges are moving towards right and negative charges are moving towards left. One is moving towards right and the negative charge is moving towards left. Positive charge is moving towards right. Negative charge is moving towards left. In which direction is the current flowing? Is it flowing in the pink direction or is it flowing in the green direction? Yes.
Pink direction.
Yes. And both of them are getting added or subtracted. We had done one question where positive and negative charges were flowing, but they were flowing in the same direction. And in that case, we had subtracted. Do we remember this? 20 electrons were going like this. 5 protons were also going like this. We found out the net charge that was going. Do we remember this question? In that case, they were getting subtracted because they were moving in the same direction. Do we understand this? Do we understand this? In this case, effectively, the current is moving towards right. So only two options can be correct. Either it can be option A or either it can be option B. The rest is not possible. We just find out which option is there. So the total current will be total charge divided by total time. Now total charge is 2.9 into 10 raised to the power 18 neon plus. So it has one positive charge. So you can multiply it by 1.6 into 10 raised to the power minus 19 divided by time is 1 second plus 1.2 into 10 raised to the power 18 multiplied by 1.6 into 10 raised to the power minus 19 divided by 1. Remember, you don't have to write so much because if you are going to write so much, you are going to waste time. This is basically charge of an electron. Both are charges of the electron. So you can just keep them in mind. You just need to add this pink number with this green number. Do we understand this? Do
Yes,
we
sir.
understand this? So
Yes.
basically this 2.9 because they are in the same powers also. Just have to add 2.9 with 1.2. If I add 2.9 with 1.2, I will get 4 something. This 4 has to be multiplied by 1.6. 4 into 16 is 64. So somewhere around 60, 64 should be your answer towards right. The only option that matches is this option, and therefore this is the correct option. This is how you have to calculate in the examination hall. You just cannot write so much. I am doing it today here because we are trying to understand it. In the examination hall, we cannot do it in this way. Anyone got the answer for this one? I'll give you 1 minute to note the question down, and then we will move ahead. Let me know once you are done. So you have noted this down, then we move ahead. And the next heading that we are going to understand is what are conductors. What are conductors? We'll write
Which
all these
allows the flow of
things.
current.
Hmm? Conductors are,
Allows the flow of current.
they allow the flow of current. How do they allow the flow of current? How do they allow the flow of current? The electrons are weakly bound. Are weakly bound. Electrons are free to move. So whenever you apply an electric field, the electrons will start to move. In which direction will the electrons start to move? Same direction as electric field or opposite direction to electric field? When the electric field is applied,
Opposite, sir.
they move opposite. And these type of things, materials are known as conductor. All metals are conductors. Whenever we talk about metals, all metals are conductor. The charge carriers, the things that carry charge in a conductor are nothing but electrons. It's only the electrons that are moving inside a conductor. There are no positive charges which are moving inside a conductor. But even though there are no positive charges moving inside the conductor, the direction of current is taken as the direction of flow of positive charges, which is opposite to the direction of flow of negative charges or electrons. Do we understand this? Yes or no? Charge carriers are conductors. You can write it in solids. Charge carrier are electrons in solids. In liquids, electrons, whenever we talk about liquid, we talk about, okay, so you just write it like this. Charge carrier electrons in solids. Charge carriers are positive and negative ions in liquids. This might come as a question. And charge carriers are positive ions and electrons in gases. Now, gases are not conductors, gases and liquids, but they can allow some current to flow, and it is because of the flow of positive ions and free electrons. So do we understand conductors? Yes or no?
Yes, sir.
Have you noted it down?
Yes, sir.
Okay, these are conductors. Then there is something which is opposite to that of a conductor. What is those? What are those?
Later.
Insulators. Insulators. So that is the next heading, insulators. What are insulators, my dear friends? What are insulators? They don't allow current. Why? They don't allow the flow of current. Why do they don't allow? No free
No free
electrons.
electrons.
No free electrons. No ions. No free electrons. They are also known as dielectrics. Do we remember the term dielectrics? Do we remember the term the dielectrics? Do we remember the term dielectrics? Okay, great. The dielectric constant lies between 1 and infinity in this case. You can also write the dielectric constant for a conductor. Let me just go back and add this point as well. What is the dielectric constant of a conductor? The dielectric constant of a conductor. How much is the dielectric constant of a conductor? K. The value of K for a conductor. Do we remember this? Boys and girls?
Sir.
What is the dielectric constant of a conductor? Okay. It is infinity. Please remember it. I have told you so many times. But every time I ask, I don't get any answer. I don't know why you can't remember it. Anyways, the dielectric constant of a conductor is infinite, whereas the dielectric constant of an insulator is between between 1 and infinity. That is known as insulators. Do we remember this?
Yes, sir.
Then the next category is semiconductors. What are these semiconductors? Anyone have heard about these semiconductors?
Partial flow of current.
At low temperatures, at low temperatures, they behave as what? At low temperatures, they behave as insulators. So at low temperatures, they are insulator. As temperature rises, they can conduct current. Their conductivity lies between conductors. Oh, sorry. I should write insulators and conductors. So they are not like insulators that they do not conduct at all, but they are also not conductors. They don't conduct very high. So their conductivity lies between insulators and conductors. Do we understand this? So they are some way in between insulators and conductors. I'll give you 2 minutes to note this down. So now let's move ahead and see what we are going to do. We have seen what are current, what are conductors, what are insulators, what are semiconductors. The next heading that we are going to write is the heading of this class that I had written, current density. Current density. Have you heard this term, current density? Current density. It's denoted by J and it is a vector. Now, current is is not a vector. Even though it has magnitude and it has direction, it is not vector. Why it is not a vector? I told you in the last class. Why it is not a vector? Does anyone remember? Why current is not a vector? Do we remember why current is not a vector?
Because it does not follow vector addition.
Good. Good. I'm happy. I thought that you will not remember. Good. See, small things can give you happiness. Uh, Current does not obey vector law. So if one current is coming from here, other current is coming from here, you can find out how much current is going in the third branch. We have seen that yesterday. But there is a vector which can be associated with current, and that is known as current density. Now, current density is a vector, so that is the first thing that we are going to write. Current density is a vector quantity. Current density is a vector quantity. Now, as soon as we hear the word vector, we must understand two things. What are the two things that we must understand? Huh?
Magnitude and direction.
Hmm. The magnitude of current density, which I write like J, is equal to current per unit area. So if I talk about the magnitude, it is current per unit area, I by A. So current density is current flowing per unit area. Current density is current flowing per unit area. That is the magnitude of current density. Then what is the direction of current density? What is the direction of current density? Direction of current density, and then I will write it as J. Direction of current density is same as the direction of current, which is the direction of flow of positive charges. Do we understand this?
Yes, sir.
The direction of current density is same as the direction of current. Now, if I write the vector equation of current density, now in order to understand the vector equation of current density, let us have a look at this short, this diagram that will help you understand the current density. What is the current density? Now, I hope you can see this diagram, a very important diagram here. Now, what do we see here is current flowing in a conductor. This thing that you see, this thing that you see is a conductor. Do you see this conductor? And you can see current flowing through this conductor. You take a small area, this pink area, this small area, this pink area. You take, can you see this, or is it too small for you to see? Do you see this? Yes or no? Do we see this small area? Do
Yes,
we
sir.
see this small area? Okay. Then the current density, you can see, my dear friends, that the direction of positive charges flow is like this. The direction of negative charge flow would be like this. Effectively, the direction of current is like this. Do we understand this? And therefore, this is the direction of current density. And if I have to write current density in this case, vectorly, this current density is written as small current flowing through this section divided by a small area multiplied by this unit vector. This unit vector eta, or you can write this as vector also, unit vector eta, which is in the direction of current. Do we understand this? Yes or no? No or yes? Do we understand this?
Yes, sir.
Have we understood the concept of current density?
Yes, sir.
Sir.
Now, first understand, then I will give you time to write. First understand, then I will give you time to write. If the area was straight like this, we can write it like this, but sometimes the area might be at an angle. And you can see here in this particular section, your area is like this. So this direction, which is the pink direction, is known as the direction of area vector. Area is taken as a vector quantity. Do we remember? Gauss law, area is taken as a vector quantity. Do we remember that? And the direction of area is perpendicular to the area. Do we remember it? Do we remember it? Area is taken as a vector quantity. Do we remember it? Yes or no? Okay. So pink is the direction of area vector. Blue is the direction of current vector, current density vector. In this case, the current density vector, in this case, the magnitude of current density will become dI divided by dA into cos theta. Or you can write small current dI is J into dA cos theta. Actually, your dI can be written as J dot dA. So that becomes your relation between current and current density. Current is the dot product of current density with your area vector. It is something like electric flux. You can take J as your electric field. You dot electric field with area vector, you get electric flux. Similarly, here you take the dot product of current density with area and you get your current. Do we understand this?
Yes, sir.
Everyone understand this? This is DI. So if I find out the total current, it will be the integral. So total current I will be the integral of G dot dA. This is exactly the same relation that we got between electric field, which was a vector, and electric flux, which was a scalar. Do we understand this?
Yes,
I
sir.
give you 2 minutes to draw this diagram. Everyone is drawing it, yes or no?
Yes, sir.
2 minutes to draw this diagram. Okay, then we will move ahead and write all these points, all these important things point wise. So what is the relation between current and current density? Small current DI is equal to G dot dA. That is the first thing that you have to remember. Then you can integrate this equation and you can get current density dot dA integral as current. Now, if current density is constant, then you will have this formula I will be equal to J dot A. Do we understand this? If current density is constant, you will get this formula. Do we understand this?
Yes, sir.
Or you can write it in this fashion. In this case, I will become J into A into cos theta. What is theta here? Who is going to tell me what is theta here? And this is the formula that will come in your case. They will not give you variable current density. I have not even seen a question in JEE up till now. What is theta here? What is theta here? What is theta here? No one knows it. Okay. Theta here is the angle between your current density, blue one, and your area vector, the pink one. Do we understand this? Yes or no?
Yes, sir.
Thank God, sir. I thought that I missed it, sir. Anyone understands this?
Yes, sir.
Pakka na, sir? Okay. Then the next thing you have to understand is what are the units and what are the dimensions of current density. Please note them down. Current density, as you know, is a vector quantity. The SI unit, the SI unit, the vector quantity. Current density is a vector quantity. The SI unit is ampere per meter square, and the dimension is L minus 2 multiplied by L minus 2 into A. Do we understand this? Yes or no? No, yes. Do we understand this? Yes or no? No, yes. I'll give you 2 minutes to write this down. So since we have understood what is current density, this is a question that I am giving you as a homework to try in the next class. What you have here is a copper wire of length 1 meter, radius 1 meter is joined in series together with a iron wire of length 1 meter and radius 3 mm, and a current is passed through the wire. What is the ratio of current densities in the copper and iron wire? We will start the next class with this question. So I request you to note down this question, and we will begin your class with this question and take things forward from here. This is a very important topic, current density, and we are going to understand some more terms in this topic in the next class, and I'm expecting one at least question from this particular section in your exam. So we will be covering that in the next class. I hope you have understood today's class. Yes or no, everyone? Everyone
Yes,
understood
sir.
what we did today? Yes or no?
Yes, sir.
Okay, then please note this question down. We will go ahead with this question in the next class. Take care and may God bless you all. Bye bye. I'll
Bye,
see you
sir.
tomorrow.
Bye, sir.
Bye bye.